All right, so we can't leave the section on, satellites and planets and motion through space without talking about rocket ships. At their heart, though, rocket ships are actually very simple. Sorry, I'm hesitating. This is just section 5.3 of the lecture notes. At their heart, rocket ships are actually very simple machines. So 5.3.1 is actually blasting off. How is it that a rocket ship actually, blasts off, leaves the Earth's surface, and makes it to outer space? In our daily lives, we often think about generating motion by pushing off against stuff, right? We push on the ground with our feet in order to walk or in order to jump. If we're sitting on a roller chair, we push against a wall. The wall pushes back on us by Newton's third law, and that, sends us rolling across the floor, so on and so forth. This kind of direct pushing against an external object is certainly one way to move around, but it's not the only way to move around, and it's definitely not how rocket ships work. In outer space, there's nothing to push against, and yet rockets are still able to move. So what are they doing? What they're doing is actually, something we've talked about before. You might remember from, I think it was chapter 3 of these lecture notes, this question of, what if you're trapped on a frozen lake with essentially no friction, right? There's so little friction that if you try to take a step, push off against the ground, you're just going to fall flat on your face. You want to make it to the shore, though, and so what you do is you take your hat and you throw it with some velocity, right? You have a mass of the hat, you've got the hat moving with some velocity, and then by conservation of momentum, that sends you, moving off in the opposite direction at some other velocity, whose magnitude is related to the ratio of these masses, right? And the magnitude of how fast you're able to throw your hat. Okay, rocket ships are doing the same thing. What a rocket ship is doing, let's see how we do here. There's like a nozzle, and there's wings, and there's a person, probably waving. And a rocket ship, as every child's cartoon drawing shows, has an engine which is expelling unbelievably hot gas, unbelievably quickly, away from itself. So rocket ships are doing the same thing as this person trapped on the frozen lake. Instead of throwing a hat, they're throwing superheated, supersonic gas molecules behind them, right? And so, again, if you like, by the conservation of momentum, there's like masses and velocities of gas molecules flying this way, and that's propelling the rocket ship in the opposite direction. If you want to think about it in terms of forces, inside the engine, the engine of the rocket ship is exerting forces on these gas molecules to get them to go very fast in, this downward direction, or if this is outer space, in whatever direction that is. So the rocket ship is exerting forces on the gas molecules, and by Newton's third law, the gas molecules are exerting forces back on the rocket ship, right? So that is how rocket ships are able to propel themselves. It's not like, this rocket plume as the rocket leaves the ground is somehow pushing against the ground and lifting the rocket up. No, the rocket exerts a force on the gas exerts a force on the rocket. And alternately, if you like, we're exploiting the conservation of momentum so that this gas that the rocket is expelling doesn't need to push on anything once it's left the rocket in order for this rocket to fly upwards. So actually, rockets operate incredibly simply, by the same principles that we encountered earlier. It's just that, there is lots of engineering to maximize efficiency. How do we shape the nozzle and construct the engine so that, these gas molecules fly as fast as possible downward? Just like in this example, the velocity that you move in the right direction depends on the ratio of the masses and also the velocity you expel your hat at. Similarly, rockets want to expel gas as quickly as possible, and they want to have it, pointing in the downward direction as much as possible. If the expulsion was really broad, you would be losing some of the momentum, at least some of the potential momentum you want to go up, by throwing stuff sideways or partially sideways instead of throwing it as straight down as possible. So rockets have a lot of engineering to kind of optimize this whole process, but at heart, it's a very simple idea of how a rocket basically works. And just to give you a sense of scale, actually the engineering is incredibly sophisticated, and the exhaust velocities of this gas, velocities of gas, can easily be like 10,000 miles an hour during, say, the launch of a space shuttle. And then there's other complicated, engineering pieces, like when you're launching a shuttle. I can't remember if I have a picture queued up or not. I don't think so. It's too bad. When you're launching a shuttle, at first, a lot of the mass of the shuttle is occupied by fuel. And so shuttles are designed so that they burn up fuel and then spit out empty, let go of these empty storage tanks so that they don't have to carry all of that extra mass with them. But it's kind of an engineering detail. So the last thing that I want to think about is the following. Rockets, this is the basic mechanism that they use in order to blast off into space. And when rockets are operating in this manner, with this expulsion of gas constantly making the rocket ship, accelerate upward against the weight of gravity, against the pull of the Earth down on the rocket ship, the rocket can continuously accelerate by exhausting, more and more gas behind it. And so as long as it keeps firing the rocket engines, and as long as the rocket engines are enough to get it to move any amount against Earth's gravity, the rocket will eventually escape from the Earth. And then it's just a question of, did you bring enough fuel with you to make it, into outer space? What I want to ask, though, is what if we wanted to know not about this process of continuously exerting forces in order to escape the Earth's gravity? What if we just wanted to build a gigantic slingshot that would just launch an object at a velocity that was so fast that it was able to escape from the Earth's gravitational pull all on its own? Something like Newton's cannon, in fact, where we saw that, if you fire the cannonball a little faster, it gets farther and farther around the Earth. Eventually it gets into a circular orbit. If you fire even faster, it gets into an elliptical orbit. Could we fire a cannonball so fast that it actually leaves Earth's orbit altogether, and flies off into outer space just by having a sufficiently fast initial velocity? So this section is asking, is there an escape velocity? An initial velocity pointed away from the Earth's surface so fast that you could escape the Earth's gravitational pull altogether. There is, and actually we can figure this out not by doing complicated calculations of, okay, I have an initial velocity and then I carefully study, I fly off this way, here's the Earth, I have a complicated trajectory as I start falling, but I'm moving really fast and, eventually I escape from the Earth. We don't need to calculate those complicated trajectories. Actually, we can just think about the conservation of energy. However, just like when we needed Newton's universal law of gravitation to get that more accurate expression for the force due to gravity when we were thinking about orbital periods of satellites, here we need a more complicated, a more accurate expression for the potential due to gravity in order to make this, in order to get this to work out. So, up to now, near the Earth's surface, we've said stuff like the potential due to gravity, the gravitational potential energy that an object has, is like the mass of that object times the acceleration due to gravity times the height of the object. And we've been pretty casual about what we mean by height. We've defined height so that it's maximally convenient for our problem. Because what we've really been doing the whole time is saying, if I'm standing over here, and I want to lift an object from this height, and lift my arm so that it goes up to this height, what we've really been asking about is not actually the exact potential energy of the object at this new height. We've just been asking about the difference in the gravitational potential energy. So we've secretly been saying something like, the change in the gravitational potential energy, is like the mass of the object times g times the change in height of the object. Okay, and near the surface of the Earth, this works really well. Just like near the surface of the Earth, force equals mass times g works really well. Okay, but Newton's law of gravitation implies not just that the actual force is more complicated, but also that the potential energy stored in the gravitational attraction between two objects is actually the following expression. It's equal to negative this g, the same constant of nature that appeared in the expression for the forces, times the masses of both objects divided by 1 power of the distance between them. Okay, so we've got all the same quantities that appeared in the force law, but now there's only 1 power of r, there's also this minus sign, and energy is a scalar, so we don't need to say what direction anything is pointing in. The energy is just some number. Okay, again, I want to ask, how does this expression square with this approximation we've been using earlier? So in my lecture notes, I do a much more careful job of plotting what is the potential, what is the gravitational potential, say, between an object and the Earth as a function of distance from the Earth's center, distance from Earth's center. And, the mass of the objects is positive, the distance here is positive, so this whole graph is going to be a negative number. 1 divided by 0, that's like an ill-defined number, so I guess it's good that two objects can't occupy exactly the same physical space. For very small distances, this kind of goes off like that, and then it kind of tapers like this. So let me try to draw this. And again, there's like a much better plot in the lecture notes. Okay, so the actual potential looks something like this. And the reason we can use the simple approximation that we do over here is that, on this scale, this is like, say, 63,000 kilometers. Like a typical distance from the center of the Earth you might be if you're sitting on the surface, or if you're on the surface. And if we zoom in on this plot in this little range, so, if we zoom in here, so that, we've got some potential over here, and, going this way is still distance. On this scale, this looks basically like a straight line. And the slope of this straight line is exactly what gives us this m times g. Okay? So this m times g is just a very good approximation to the fact that so far away from the Earth's surface, in a narrow range near the Earth's surface, this whole kind of complicated shape really looks very close to a straight line. And so we can approximate the true potential with kind of the simpler expressions we've been using. And for most of the stuff in this class, those simpler approximations are going to be totally fine. Now that we have this kind of expression for what is the actual potential energy, not just an approximation that is good for describing changes in potential energy, but what is the actual potential energy stored due to gravity, due to the gravitational attraction between two objects. Now we can actually work out the escape velocity just by thinking about conservation of energy. Via conservation of energy. So, what do we want to have happen? We want to have like an initial state of our system. Okay, we're targeting some final state. We want to have an initial state where, there's some amount of kinetic energy, and I'll just call that 1/2 times the mass of the object we're firing. So I'll call that, m1, times some escape velocity squared. We want to know, is there a velocity so strong that we'll be able to escape the Earth? And in our initial state, this is how much kinetic energy we'll have. And we'll also have some gravitational potential energy. And from our expression above, that will be like minus g, times the mass of the object times the mass of the Earth divided by r, right? Where that r will be like what is the distance from the center of the Earth, wherever we're firing this object from. So this is the initial energy our object is going to have when we first fire it off of the Earth's surface. Okay, and what do we want? In the final state, I want to imagine that we've fired this object just fast enough that it's just barely able to escape the Earth's gravitational field. So in the final state, I want to say the gravitational potential energy, is zero. We've escaped the Earth's field. We're so hugely far away from the Earth that we've lost all of this potential energy. And if I want to find the break-even point of how fast do I need to fire so that I'm just barely able to escape the Earth's velocity, I want to think about a case where all of my initial kinetic energy went into getting rid of any potential energy that I had. So I want to get to a final state where I've just barely escaped the Earth's gravitational field and I've slowed down to where I have no more velocity anymore. So we can think about this process, again, as I want conservation of energy because I know energy is conserved. Let me consider these two forms of energy my, say, cannonball initially has. And then conservation of energy says the initial energy is equal to the final energy. And I've arranged things so that, the final energy is 0 kinetic energy plus 0 potential energy. And the initial kinetic energy, or the initial energy, is 1/2 times m1 escape velocity squared plus the gravitational potential energy, and that's minus g m1 m Earth over radius. And once I've done it this way, just by thinking about the conservation of energy, not worrying about the complex, actually in this case hyperbolic trajectory that the object will follow as it escapes the Earth, we can just rearrange this equation to see that the escape velocity is going to be equal to the square root. So if I move this to the other side of the equation, I multiply by 2, I divide by m1, the mass of the object itself doesn't matter for the escape velocity, and I end up with twice the mass of the Earth times this gravitational constant divided by how far from the Earth's surface was I when we first fired this object off. Okay, so there you go. If you don't want to use a rocket ship to escape the Earth, but you just want to throw an object fast enough that it escapes from the Earth anyway, conservation of energy and thinking about this more general expression for what is the actual potential energy stored in the gravitational attraction between two objects, you can work that out just by thinking about these basic energy conservation concepts. Okay, that's fantastic. Okay, so that wraps up the last of our section on mechanical objects, and when we get to the next chapter after the midterm, we'll start thinking about fluids. So I'm looking forward to that.